Griffiths section 2.3.4, example 2.8. The goal of example 2.8 is to find the potential at some point in space from a uniformly charged spherical shell of radius r. Okay, so because this spherical shell is uniformly charged, I can put it at whatever orientation that I want to on my coordinate system, and I'm going to center it at the origin. Now, you have done a similar problem in the previous example by using Gauss's law to calculate the electric field. But the goal here is to use this charge distribution directly to find the potential. Okay, so perhaps you could do this in a different scenario where you didn't have the symmetry that allowed you to use Gauss's law. And this would be one of your only viable options. Okay. So I want to know what the potential is at some point in space, and because my spherical shell is uniformly charged, I can pick any arbitrary point in space without loss of generality. So I'm going to pick a point on the z-axis that I want to measure the potential at. So let's say that's a distance z away from the origin. And the charges exist on some patch on the surface. Those are a distance r away because they're on the surface of my sphere. And my script r vector points from the charges to the point that I actually care about. And we're going to take advantage of our law of cosines here to say that, all right, this is an angle that separates my two vectors, the vector that points from my origin to my charges, more to my point in space that I care about, and the vector that points from the origin to my charges, right? Because I said that was script r. Now, one nice thing about these integrals is that as opposed to the electric field integrals, we don't have to care so much about vectors anymore. We can just find the magnitude of script r. And once I have the magnitude of script r, I can go ahead and find the electric potential using the integral expression we derived in the last video. So this is a surface charge. So my surfaces exist at some point in space, and I must integrate over at that point in space. That's not an integral, and not a vector. And I need to know the distance between all of those points. So I know that script r squared is equal to r squared plus z squared minus 2rz cos theta prime. So I can plug that in to my expression for my potential, 1 over 4 pi epsilon naught. I have sigma, which doesn't depend on space. I have my dA. Well, the dA is r squared, capital R, because that's where my surface lives, sine theta prime, d theta prime, d phi prime, all over r squared plus z squared minus 2rz cos theta prime to the 1/2. All right, so I can do the phi integral pretty easy because there's no phis anywhere. That gives me a 2 pi, because I want to integrate over the whole surface because that's where the charges exist. So I get 1 over 4 pi epsilon naught, 2 pi. I'll pull out some constants here. I'm left with the integral of sine theta prime d theta prime over r squared plus z squared minus 2rz cos theta prime to the 1/2. So this is the point in time where I go to my integral solver. I prefer to use Wolfram alpha. It doesn't matter what you use, but the important thing is I need to know what the bounds are. Okay, so my bounds for theta, which is my polar angle, must go from 0 to pi. So if I then plug that in, I'm going to go ahead and write that the potentials at some point in space is z, but it doesn't really matter because our sphere is uniformly charged. That is 2 pi sigma r squared over 4 pi epsilon naught. I get a 1 over rz from my integral, and then I have this expression r plus z squared and the square root minus r minus z squared in the square root. Now I haven't specified exactly where on my z-axis I'm defining my point that I care about. So what in the end what I want to do is I want to measure the potential or find the potential everywhere along my z-axis. So sometimes that means that I'm outside of my sphere where z is bigger than the radius of my sphere, and sometimes which I'll probably have to do over here, sometimes I'm going to look inside the sphere where z is less than the radius of my sphere. Now the difference in this result is that we have to be careful about how we evaluate expressions like this. So we have to always take the positive root. Right? So when I have to take this solution, sometimes that gives me r minus z, and sometimes that gives me z minus r. And I have to pick the appropriate choice depending on the condition, if z is bigger than r or z is less than r. Right? I always want to take the result where that value is positive. So for z greater than r, I write down that v of z is equal to 2 pi sigma r squared, 1 over 4 pi epsilon naught, 1 over rz. That first root doesn't matter, that's always a positive value. So that becomes r plus z. And then I must take the positive root. Z is bigger than r, so that must mean I get z minus r here. All right, I'm going to distribute this negative sign in, and I get the z's cancel. I get 2 r's. So I get 4 pi sigma r squared over 4 pi epsilon naught, 1 over z. Okay, I've left a bunch of 4 pi's in there, and I could simplify that, but let's leave them in there for a second. Okay, so for our other case where we're inside of our sphere, I have to take the other root. So v of z gives me I must have already canceled some stuff. 2 pi sigma r squared over 4 pi epsilon naught, 1 over rz, get r plus z, minus, now I have to take the other root, the one that's positive in this scenario, r minus z here. Okay, distribute that in. I get that the r's cancel this time. I'm left with 2z. So I get 4 pi sigma r squared over 4 pi epsilon naught 1 over rz times, oh, I already took that 2 inside there, times z. Z's cancel. I'm left with 4 pi sigma r squared over 4 pi epsilon naught r. Okay. So the reason I kept these extra cancelable terms in here is that this 4 pi sigma r squared, well, 4 pi r squared is just the surface area of a sphere, and sigma is the charge density. So if I multiply the surface area times the charge density, I get the total charge. So let's assume that the total charge is equal to Q. I could write this as Q over 4 pi epsilon naught 1 over Z. Same here. That's just Q. This is Q over 4 pi epsilon naught 1 over R. Okay. And hopefully that looks familiar, right? That should be what you calculated last time. This is outside of my sphere. I have something that depends on my position, and inside of my sphere, I have something that doesn't, right? The potential inside of my charged surface is constant.